Good morning, everybody. Welcome to another episode of Algo Talk. I'm here with Errichto, and today we'll be talking about his problem, New Year's and cleaning.
Hello, good to be back here.
So this was a problem in the Goodbye 2015 set that Errichto was an author for, a problem setter. And it's a pretty interesting problem. I read it earlier and thought about it a little bit, but I don't have like a complete solution. So he's going to be kind of helping me work through it and find a path to the solution. And then we'll be doing a similar problem on his channel as well. Or not a similar problem, but like a different problem from Facebook Hacker Cup. So feel free to check that one out if you're interested.
And for this one, for New Year and cleaning, we can maybe start from some drawing explaining what the statement is about.
Sure. So, well, correct me if I'm wrong, but I'll give my summary of what the statement's asking, and then you can let me know. But you start with a 2D grid, right? With several rows and columns?
Height of H, width W. And this is a big empty grid. Size is up to 500,000 by 500,000. And we are additionally given a string describing some moves. Obviously, we aren't given this whole grid in the input. We are just given H and W, the dimensions of the grid. And there is a string consisting of characters denoting directions, left, right, up, and down.
So basically, if you start at some given position, maybe you start like here, for instance, then you'll follow this string, right? So you'll go first left, and then you go right, and then up. But now we want to go right. But if we were to go right, we would kind of fall off the grid, right?
Indeed. So we stop now, and apparently here we made 4 moves. There are 4 blue arrows. We count that as 4 moves.
Awesome. So now, in order to make sure we clean the entire house, we're going to start doing this path at every space in the grid. And we want to know, after doing that for every space, how many moves will we have made in total?
And it doesn't matter if we already visited all cells to some moment. No, it's just that for every cell, we consider that to be the starting cell, and we repeat this string on the right forever. In particular, if we get to the end of the string, we start again from the first letter. We go on and go on until we hit one of 4 walls of the grid.
Future David from the editing booth here. There's one more thing we forgot to mention, which is as you follow this string, if you ever reach the end of the string, but you haven't fallen off the board yet, then you go back to the beginning of the string and keep executing instructions from there. So it's not just execute all of the instructions at most once. After you get to the end of the string, you'll loop back around and you keep doing that all the way until you fall off the board. So it's possible that you might execute an infinite number of instructions, and in that case, you just print -1. Sure. So I guess maybe one idea that I had as far as like counting the total number of moves is if we can quickly figure out, like maybe this solution doesn't quite work because it's going to be too slow. It's going to be n squared, or width times height. But if we can figure out width times height times log, actually. But if we can figure out when the first time that we step off the grid is, then we could iterate through that for every position, and then we could maybe figure out what the total time is, because it's just the sum over all of those.
Mm-hmm.
So
I don't know if you said that. The answer is the sum of the number of moves over all possible starting cells.
Okay, yeah, good point.
We can think how to, for a single starting cell, figure out the number of moves.
So maybe if we're looking at it for a single cell, I guess one thing to keep in mind that might be important is these borders are all axis aligned, right? So they're all either like a left border or a bottom border or like a top, but they're a pretty predictable shape. So we can maybe use that. And then I guess maybe another thing that matters is like if we're always strictly inside some bounding box that maybe looks like this, then we just care whether our bounding box intersects this blue border.
Yes. If this is a bounding moves of our positions so far, that the situation is just that eventually this will exceed one of the walls. By the way, if it goes forever, and this is possible, like if we keep going left, right, left, right, left, right, then we print -1 to the output.
Okay, so yeah, so in this case, like the bounding box would never, assuming you ended up in the same position, it would never, never actually change.
Yes.
So it would never exceed where you would end up being. So in this
It
case,
happens if you end up, after repeating the string once, if you end up in the starting position and you didn't hit a wall at that moment.
so maybe
For
your
example,
path looks something
exactly
like
this.
that. Yeah.
Yes.
Interesting. Okay. So, well, what we can do is we can calculate what the bounding box is after just like each step in these moves, right? So for just one step, the bounding box is just going to be your square. But then after you like take that one step, then it'll expand in some directions, maybe something like this. And then in linear time, you can walk through this entire string and then maybe figure out what the bounding box would be for each of these steps. So maybe partway through, we've got this red bounding box.
Mm-hmm. Yeah, but what then? How to quickly handle all the next repetitions of the string?
Yeah, that's a good question for sure. So, I guess maybe one thing that we would want to check is for like this entire string as a whole, will it end up back in the same position that it starts with? Because if it doesn't, then I guess that's kind of a separate case. We don't really need to worry about that as much. And that's pretty easy to check. Basically, just the number of lefts has to equal the number of rights, and the number of ups needs to equal the number of downs.
If we keep track of our current position, then what we care about is where we will end up at after processing the string once. Green dot is now the starting cell, and there will be somewhere in the grid, there will be the ending cell, let's say. And this gives us some kind of shift vector. Is that repeating everything once will shift us like that. And if we repeated this again, then again we would be shifted even more by 2 cells to the right and 1 cell up.
Sure, yeah, that makes sense. So, yeah, so that makes sense where if you have like some pattern that's maybe a bit longer, maybe something like this, for instance. If you do this whole thing again, then you'll wind up going like this again. So you would take this blue path then the second time, or this path here.
Our bounding box this way moves quite in a predictable manner. We know what will be the bounding box of second repetition, of third repetition.
Sure. So I guess maybe I'm not totally like super comfortable with how the bounding box changes, so maybe that might be a good thing to talk about now. So let's say the bounding box is first what this red thing is. So I guess the pattern would need to be a little bit more complicated. So maybe let's make a pattern that would give us this bounding box. So that would do it.
That works.
So then if we did this a second time, then first we shifted it like this. I guess I'll draw this in green maybe.
With a different color. Yeah, starting cell is the same, but shifted by 1 to the right and by 1 down.
So then
the bounding box will also be shifted.
So yeah, so it'd look like this after the first step.
This is a second bounding box.
But then since it's only axis aligned, we can just take the minimum of the left coordinates and the maximum of the right coordinates to just get the big outer bounding box.
Yes. But it's enough. We don't need to keep track of updated big bounding box. It's enough to know bounding box of second repetition. And just because this, we know how this moves, we know which bounding box will get out of the grid.
Sure, yeah. So
and we can do it either with a formula or with binary search. I'm spoiling this because anyway we will move to some other solutions in the near future. But here, if you know that every time the whole bounding box moves by 2 to the right, let's say, you are 10 units away, then you know 5 repetitions you will hit the wall.
Yeah, okay, that makes sense. So if that's changing by like an entire group of these moves, right? But we still have the subproblem, I guess, of like if you change by some group of these moves and then some prefix of the moves within a group, I guess you still have to intersect two bounding boxes, but that doesn't seem too difficult. That's more just like just two
The
bounding box intersections, I
bounding
guess.
boxes help in checking which repetition we need, like how many full repetitions of the string we need to process. Because at the end, to simulate one last string, we can just maintain our current position and move, by one to the right when we have character R and so on. We just detect when we get outside of the grid.
Sure. Okay. So yeah, very cool. So I guess that's kind of like some general path of like how you might approach the problem if you want to iterate through each position. But I guess maybe it might be more helpful to start thinking about it instead of iterating through each position, maybe what we can do to actually approach a solution that's faster than like width times height time.
Indeed. It's almost the case that we can forget about our solution up to this moment and just try to come up with something completely new. Because the already described solution has complexity. We need to iterate over starting cell, so h times w times length of the string n. And each of those values is almost a million, so no way that will pass.
Yeah.
What about this? The first character of the string is r. Now, if let's say to the output, you need to print a lot of values. For every starting cell, you need to print how many moves there will be. So now if you draw an empty grid again, are you able for some starting cells to already say the answer? Only
Yeah, so
knowing that the
for
first
all
character
of this entire right column, you know the answer here will be 0.
0 or like 1, because we
1, yeah,
make
sure.
one move. Whatever the statement specifies about that can be 0. Now, what when the next character is up?
So then for all of the characters on the top row, all of them will be, I guess, 1 in this case. Except for this top left, which will be 0, like we decided earlier. So
And try to continue this idea.
sure, yeah. So then if after that, then we see a down, then we know nothing actually changes because we're just somewhere in this position here. And then after that, if we see another down, then that would mean that all of these would be 3.
We need to keep track just of the current cell, like how many times we moved up minus how many times down so far. Whoever we this way reached new height, this means we expanded the bounding box if we start just anywhere. And every time when we expand bounding box, it will just mean for some new row or column of the grid, we know what is the answer if we start there.
Sure, yeah.
And what we have already is enough for you to solve the problem if we don't repeat the string.
The tricky part here is now if we have some really long string, but only like one part of it at the end maybe means something new. So in this case, we travel back and forth like a bunch of times, but it's not until the very last step that we actually like extend the bounding box. So now the question is, how do we handle something like this?
Indeed, for every string, it can be detected which characters are very important because they will keep expanding the bounding box. Like here, it's obvious for us that because something is repeated so many times, it's just that last character L will move us more to the left than we were ever before.
Yeah. So I guess expanding the bounding box is like pretty straightforward because if we have some, well, I guess maybe initially, like the first time we do this, we'll see these two, or this first R will expand the bounding box, and then at the very end the L will. It's kind of weird this shows up, but
The second character is not important. L is
Because it
not
doesn't.
important.
Okay, yeah.
Only in the first run, R is important. Starting from the second run, well, actually, also in the first run, the last L is important. It will do something.
But then I guess like it's always true that for the second run, the like these things will all be filtered out, right? Like it might be important for the first run but not the second run, but it'll never be important for like the third run but not the second run, right? Or the second run but not the third. So we could
Second run is the first regular run. In the first run, anything can happen because we start from 0, 0. But after that, we have some bounding box. The second bounding box will be just the same but shifted to like, yeah, exactly, bottom right. And then the same thing will keep going on.
and then we know like within the second bounding box we're not gonna, or the second like step, we're not gonna leave this bounding box. So if we go like over here, that's not going to be important because we've already been there. So that's very understandable how
To
that would work.
simplify this, only in the first run we would have situations with going to the left or up and hitting a wall. But again, this is a simplification, but in the drawing from a moment ago, from second run onwards, there will be those important moments about hitting a new wall when going to the right or going bottom. That's a more general case.
Sure. Okay. Yeah, so that makes sense. So then I guess maybe looking at this from kind of the perspective of like taking several steps, we want to see for each of these new steps, we can only take a like linear number of these new steps, right? The bounding box can only increase a linear number of times before it doesn't fit on the board anywhere. So if we can like,
because we still continue the answer, what happens with the answer is we imagine that big grid from the previous solution and we mark one row or one column because we know the answer for that row or column. So yes, this will happen only H plus W times at most.
because like each time you remove either like you either cut off some Y or cut off some X. So yeah, that makes sense to me. So now, I suppose the question is, I guess, just like how do we identify when this happens and then which direction it happens for?
This can be implemented with a very short code. So just try to figure out what variables it will be good to maintain. What do we need?
Well, the second time it matters which we need like some array of all of the positions that are significant. So in this case, for the second group, it would be just this L at the end.
We need to know, we need to just in a brute force way run the first run, iterate the string once, do it again, and in that second run, we save positions when something interesting happened. And for the first time, we expanded the bounding box. The bounding box just means that we maintain, assuming that we start from 0, 0, maintain the current X and Y, and maintain maximum and minimum X and Y. Whenever you increase maximum X, like maximum X was 5, now it becomes 6, it means that we just made a move to the right. And if this was second run, then in the third run, fourth run, fifth run, this will make something, and we need to update the answer.
Yeah, that makes sense to me. So then in total, then since we know the bounding box will expand in each of these cases, then every time we iterate through some position in the array, we like can account for that by one of our 1 million decreases that we can do. So then we could solve it in linear time after that, right?
It's of n, length of the string, plus h plus w. H plus w comes from how many interesting operations we need to handle. N comes from simulating the string twice.
Yeah, it makes sense. So I guess this is kind of like 2n if it is easier to think about that way, maybe.
Obviously, 2 doesn't matter, but
yeah,
it's maybe easier to read.
All right, cool, very cool. So, unless there are any other details about the problem, thank you for the problem and for the test data and preparing it, everything for the code forces round. So yeah,
I
it was
will
interesting. I
just
enjoyed it.
I will just say for the viewers that we can also solve this problem if grid size is up to 1 billion. Just because everything happens in such a regular way then that you can do stuff with formulas. You do the same thing for first and second run, but there will be some arithmetic series involved. If we see that something happens in the fifth operation of second run, then third run, and so on, those indices create arithmetic series, and something regular will happen. But we shouldn't go into detail. Those formulas are ugly.
Yeah, and I guess like quite a bit of it would be making sure you've got all of your ceilings and floors right everywhere, and it's a little bit messy.
That's always a pain. But this problem can be solved in O of n. It's possible. Read this as a challenge. It's actually described in comments below Codeforces editorial for this problem. Did we say the name of the problem, or did we show the statement?
Yeah,
Yes.
so it's New Year's and cleaning right here from Goodbye 2015.
It's always in Codeforces on the right there is tutorial link. You can just scroll to the comments and you will see some more information about this problem if you wish.
Awesome. Well, thank you very much, Errichto, for joining us and for the interesting problem. And make sure to go subscribe to his channel. I'll have a link to it in the description. So yeah, thank you for joining.
Thank you, and see you in my video as well. Bye-bye.